Hi, in this video we're going to do a practice problem of kinematics in 2 dimensions. You'll see that this is a combination of what you did in Chapter 2 with the addition of vector mathematics. So take a moment to read the problem. And so we see a picture here. There's a car, a go-kart, and it's going to start right here. And it's going to go drive in a circle and end at this position, right? So the first thing we want to really do when we're looking at problems like this is draw a picture of the motion and identify some important aspects of it. So the first thing I want to show you is what we call the trajectory. That's the path that the object actually moves along as it travels. And so it's a section of a circle here, right? We start here and we end here. And you always want to identify the start and the ending points. So again, we call that the trajectory, or just the path that the object actually takes. Now we're asked to draw a displacement vector and calculate its x and y components. So quickly, let's take a look here at the definition of displacement in 2D. It's a vector, right? Here it is. And it's got 2 components, delta x, which is x final minus initial, and delta y, which is y final minus y initial. And the 2 components, their magnitude is related using the Pythagorean theorem as we learned in our study of vector math. So the displacement vector is a vector that starts at the initial position and it goes a straight line and ends at the end position there. And we can go ahead and put the arrow tip at the end to indicate that that's the direction that it points in, okay? And we can label this vector delta r. That's how we write it. What we're really interested in here are the x components of all these vectors. So let's make our table of vector components. So here we go. And first one we'll do here is delta r, and we're going to want to have a x component and a y component. Now we're going to look at that delta r vector. We want to figure out its components. What do? We're going to go ahead and graph that at the origin of a coordinate system, just like we learned for vectors. Okay, so I've just plotted the displacement vector in its own coordinate system. There you see it. Now we need to figure out what the components are. Well, going back and looking at the triangle here is going to help us out a little bit. So check this out. This is a section of a circle here, right? So this is a nice little right angle, and this is actually an isosceles triangle. We know 45, 45. If we want, we can go ahead and use that to draw our vector components. So I'm going to choose this triangle here. There's the x component, and we call this delta x. And here, going up, there's the y component. We call that delta y. And we already know the angle of this vector from the picture, 45 degrees. And the hypotenuse of the triangle, the magnitude, is delta r. And so we've got a picture of our vector. Now for this one, it's kind of easy to just look at the diagram and figure out. Look at, there's 50 meters here, right? So delta x has gone in the negative direction by an amount 50 meters. That is our delta x. We can see that. For delta y, we've gone up, right? And so for delta y, again, this is the radius of the circle here, right? So this is 50 meters. Okay, cool. And so we've got our 2 components there for delta y and delta x. We can write them down. The x component, delta x equals minus 50 meters. The y component, delta y is equal to plus 50 meters. Is the quadrant right? Let's check it. This is the second quadrant vector, right? So it's going to be negative x, and it's going to be positive y. Good, we've got that right. Okay, next step, we're asked figure out the magnitude and direction. So let's do the magnitude first, right? We're just going to go ahead and do the Pythagorean theorem. So Pythagorean theorem, the magnitude delta r is equal to delta x squared plus delta y squared. Let's plug our numbers in. All right, there's our numbers, and when we put these into the calculator, we're going to get a positive magnitude equal to 70.7 meters. So that's your magnitude, right? Now for the second part of part A, we are asked to find the direction, and we're going to specify it as an angle counterclockwise from plus x. So that means we're going to go ahead and, start at 0 degrees and move counterclockwise, right? Well, if we do that, we start here, count up 90. Plus how much more? Well, we know that this guy right here is 45, and so this must also be 45 degrees. And as we continue, 90 plus 45, that gives us the value that we're looking for, and so it's going to be the direction. 90 degrees plus 45 degrees is equal to 135 degrees counterclockwise from plus x. And so now we've figured out both parts of A. To do part B, we're going to calculate the average velocity. And so a couple things to note here. The definition for average velocity, you can see it over here. It is a vector now with two components, and one is delta x over delta t. This is your definition in Rule 1D, Chapter 2, but it's got a second component in the y direction, delta y over delta t. And as usual, these two components, since they're components of a vector, they are related with the Pythagorean theorem to the magnitude of that vector, okay? So we're going back here. We see that to calculate the components for delta, for v average, let's go ahead and write down our v average vector here. There it is. And so we're going to look for v average x, and we're going to look for v average y. Now, go back to the definitions, right? Vx average, it's equal to delta x over delta t. We know what delta x is. It's minus 50 meters here, right? Now, for delta t, we are given the value. There it is, 5 seconds is the time it takes to go from start to end here. And so we put the 5 seconds in there, calculate, and we get an answer. Minus 10 meters per second. That's your x component. Let's look at the y component. Same process. Definition here is delta y divided by delta t. Notice delta t is the same in both cases. It's a scalar. It never changes. But delta y now we know is equal to plus 50 meters. When we go ahead and calculate this, we end up with a positive 10 meters per second. So we've just got our two components here, and we can go ahead and write them down. So kind of filled our table out. We just got the first two parts of question B. Now we need to go ahead and do the magnitude, right? So it's the same idea as we've done before. If we want, we can go ahead and plot that vector too. So I've drawn a new coordinate system, and let me go ahead and plot these. So we've got minus 10 meters per second here along the x-axis, and we've got over here plus 10 meters per second squared, right? So those are the points in the plane that we're going to use to figure out where that vector ends at. There it is. And let's go ahead and draw that vector. It's going to go start from the origin, straight out to the point where it ends. There we go. Give the tip over there. We're going to call this our oops, let me get that right. V average vector. And we know a couple things about it, right? We already know, for example, that here is your x component, right? There it is, Vx minus 10, Vx average. Here's your y component. Vy average is equal to plus 10 meters per second. And so we've got our little vector there. Here's our right triangle. Here's the magnitude. Just remove the vector symbol. And to calculate that magnitude, we can go ahead and use the Pythagorean theorem as usual. So for this one, V average, the magnitude, again as usual, Vx average squared plus Vy average squared. Now let's put the numbers in and calculate. And so this is what we end up getting. The units meters per second are correct. So this is the magnitude that we wanted to solve for. Finally, we need to look for the direction. And we're going to again use counterclockwise from the plus x-axis for this one. So if we look at this, there's a few ways to look at this here. So I'm going to try to identify this angle. Now you might notice that this is also an isosceles triangle, and so we know that that's going to be 45 degrees. But we can always use the method we learned for vectors. Let's try it. So to calculate that angle, we're going to use the inverse tangent function. And for this particular angle here, the opposite is Vy, the adjacent is Vx. And so we're going to go ahead and use those two values, opposite, oops, let me get my color, opposite divided by adjacent, okay? Now, again, I'm not going to worry about the negative signs. Just take the absolute value, and I'll just get an angle between 0 and 90. So if I put the numbers in, we're going to have 10 divided by 10. I can ignore the units because they cancel. And when we go ahead and calculate that, I'm going to get a value of 45 degrees. So it's 45 degrees, as we could have already figured out by looking at the triangle. But you can always do it like that. Now to specify this as an angle counterclockwise from plus x, we got to start over here again, 0, 90, and start to move until we get to the vector counterclockwise. So counting up, 90, keep going, keep going. What do we get to? Well, we could think of it like this, right? Go all the way to 180 and then go backwards by 45, and so the angle that we're looking for here, it's going to be all the way to 180, go backwards by 45 degrees, 135 degrees. So we've got the direction of the average acceleration, we've got the magnitude of the average acceleration, and we've got the components. Let's check. This is also a second quadrant vector, and so we see that, all right, we got the negative sign for the x and the positive sign for the y. Now you may be wondering why it is that the directions are the same for both the displacement vector here and for the average velocity vector here. Well, it's no coincidence actually. If we go back to the vector equation here, v average vector equals delta r over delta t. Because of this equation, right, delta t, it divides delta r, but it's a scalar. It can't change the direction of delta r. It gives v average new units because it introduces seconds, but the fact that this vector is proportional to delta r, these two are always going to have the same direction. All right.